Next up, we have Theo Wang talking to us about typed abstractions for causal probabilistic programming. Thanks.
Yes, okay. Hello, everyone. Welcome to my talk. So I'll be talking about typed abstractions for causal probabilistic programming, and just joint work with Dario, who is here, and as well as Eli, Jack, Ohad, Michael, and Jeremy. So I want to start by putting our work in some context, right? So causal inference, or causal reasoning in general, as already mentioned previously, is this mathematical toolkit developed by Perl to reason about causal relationships, like does X cause Y? Or given that we saw Y, had X not happened, would Y still have happened? So this toolkit has wide applications in empirical sciences and most recently machine learning and, well, in everything that really requires you to talk about causal relationships. Causal probabilistic programming is this programming paradigm that's developed quite recently, which involves extending a fully fledged probabilistic programming language with first-class causal primitives. So the idea is then to be able to perform causal inference on general probabilistic programs. So there's a couple of examples of languages that meet this description, including Multiverse, Omega C, as well as ChiRho, which is the one we're going to focus on today. It's this Python library developed by Basis that I think was also mentioned briefly in the industry talk. And our contribution is that we made ChiRho into a Haskell library. And that meant that we had to first disentangle its cool features from the implementation concerns, like well, it was implemented using Pyro's effect handlers and vectorization. And also it was in Python, so untyped, so we had to make all the abstractions typed. And by doing so, we have obtained a much clearer description of what its semantics looks like. And this is what our talk, this is what how this talk is going to be structured. So we'll start with the crash course in causal inference with a small example, and then we'll show you how to use typed abstractions to actually solve this problem in the ChiRho style. So, right. Let's start with a small example. Say Dario has a car, right? And it's represented with, so the probability of it starting is represented by this probabilistic program. So it starts if it has fuel and battery, and it has fuel with probability 0.8, and independently it has battery with probability 0.9. So Dario is quite unhappy today because his car didn't start. And we want to ask, had he refueled, would the car have started? And the first thing we want to notice here is that this query is not quite a probabilistic query. You can't directly solve it with probabilistic programming because, well, firstly, this doesn't even talk about just one model. It talks about somehow two copies of the same model. We have a factual one where Dario's car didn't start, in the real world, and a counterfactual one where we are asking if he had refueled, would the car have started? And in fact, what we're doing on the factual world is what's called observation. So it's the same, it's conditioning, right, in probabilistic programming, just saying, OK, we condition on the fact that Dario's car didn't start. But what we're doing on the counterfactual world is not observation. It's what's called an intervention. So intuitively, it means that we're not observing that Dario hasn't refueled. What we're doing is the equivalent of going back in time and forcing Dario to refuel his car while keeping everything else the same, and then asking, OK, would the car have started in this scenario? So how do we answer this kind of query systematically? Well, this is exactly what Perl's toolkit is about. And the idea is to transform the original model that we have into another one, such that if you do inference on it, it will produce the answer to the causal query we're after. So we would be reducing the causal query into a probabilistic one. And so if we start with our original program at the top here, the first step we'd do would be twinning. So this is a program transformation, or naturally presented as a program transformation, perhaps. And the point is that we want to create these two copies of the same world, right, while keeping everything else as much the same as possible. And this is exactly what twinning is about. And as you can see here, we have created, well, OK. No, I'm not going to use this mouth. So as you can see here, we have like two copies of the same model such that they are correlated in some appropriate way. In this particular case, the key attributes that we're sharing between the two worlds would be fuel and battery. And these would be called exogenous variable in Perl's presentation. And then once we have this twinned model, all that we have to do is observing on the factual world and intervening on the counterfactual world. So this is what we get. Observing is easy, right? We know how to do conditioning, just add a statement at the end. But intervention's a bit more involved. You have to use program transformation, where we have to find the counterfactual copy of Theo and then set it to true. So then if you look at what we have at the end as a, if you look at the model that we have at the end, then, well, this is basically what we expected. We have two worlds, a factual one and a counterfactual one. And then on the counterfactual one, we have intervened on Theo, but kept everything else the same. And so now if you run inference on it, you get about 64%, which is, by the way, the answer to the question that we had. Right. OK, so let's stop and think what we did here. We have reduced our causal query into a probabilistic one by successfully applying these program transformations, so these causal operations, on the original model. And in fact, all of the causal operations that we have given were presented as these program transformations, which is nice to some extent. But then also, program transformations are very subtle to deal with and don't necessarily compose very well. So we don't really want that. And what we want instead is to have a language that has these these causal primitives as first-class operations, such that we can perform these operations, these transformations automatically, but also in a way that is safe and compositional. And as you've guessed, we'll do this by having a typed version of ChiRho, the probabilistic programming language developed by Basis. Right. So this is what the second half of the talk is going to be about. I'll give you a taste of what the abstractions are like. OK. So OK, firstly, let's think about how to implement these interventions. Right. The idea is to not allow interventions on arbitrary points of the program, but instead only allow them at these specific points we call intervention points. So these intervention points will be these program locations where we allow interventions to happen, right? And formally what we do is, we create this monad called the cause monad, which will represent all of the the causal models. And this is basically, as you can see, a reader monad transformer on the probability monad. And this additional environment that we're taking here should be thought of as this map in the programmatic sense from intervention points to lists of intervention instructions. What that means is that a model is now this suspended computation that is executed on an environment. And this environment contains, for each intervention point, all of the interventions that you're inserting in this program. So concretely, in a model, this is what it looks like. So at line 5 here, we're creating this new intervention point for the original fuel value. And what this says is basically that, this new operation creates this new intervention point. It takes an identifier called fuel point. And then what it does on this fuel value is that, it takes it, and then it reads from the environment, gets all of the intervention instructions that are associated to this intervention point, and then applies them on fuel. And fuel enters the return, with what comes out of applying all of these interventions on fuel. And the good thing about presenting things this way is that instead of doing program transformations, we can just formulate the idea of inserting an intervention in a program as doing a transformation on the environment. And for example, here, if we want to insert this intervention instruction at an intervention point, then all that we do is, we take an environment and insert it at the corresponding entry in the environment. And then to apply it on the model, all that we do is just precompose the model with it. So it all becomes very clear, and we don't really need to do any program transformation anymore. So what about twinning? So twinning is a bit more involved, actually, and we don't really have time to talk much into it. But basically, what we're doing, the strategy is to automatically perform twinning by eagerly computing all of the worlds that we are actually interested in at the same time. And the first question, of course, is, what worlds do we want to use? And basically, those worlds will be determined by the interventions. Like, for example, if we have one intervention, then we're interested in two worlds, one factual, one counterfactual. If we have two, we're interested in four, etc. And then how we do this is by using an applicative called multivalue. I won't give much more detail in it. But yeah, come find me at the poster session or a bit later if you're interested. And right, if you put everything together, this is what the program would look like to solve that exact same problem. And the point is that the model code here, the code here is very clean and simple, right? So the model is exactly what it was before, except we're threading through this this applicative to do the twinning automatically. And we'll also added on line 5 here an intervention point so that we can do the intervention on fuel. And then the inference is also very simple, right? So you take, so basically what you're doing is, well, you take the model and then apply the intervention on the model here. And then once you have the intervention in the program, the twinning will be happening automatically. And all that you have to do is to get the factual value of whether the car starts and condition it to be false, and then return the counterfactual value. And now if you run inference on it, if you run inference on it, then you get exactly the right answer, which is about 64%. Right. So, OK, to conclude briefly, we've started by presenting these causal operations in Perl style as program transformations, but then we saw that actually we could do them automatically and safely using some typed abstractions that we created by taking inspiration from ChiRho, where you have this interventions as a monad, a reader monad, and twinning as this applicative. And this is actually very highly expressive, as we have a lot of examples in the implementation if you're interested. And this is also our first step towards giving a more general semantics to causal probabilistic programming. Yeah, so if you're more interested, I'm here at the poster session. Dario is also here, so yeah.
Thank you. Time for one question, and for the next speaker, please get ready.
Thanks for the talk. It looks like you still have a little bit of program transformation to do if you want to do intervention, where you have to add these points in the original program, right? The intervention points.
So to some extent, yes. But then,
so the question is, could you just take all the random variables that are defined in your program and declare them as points? So
yes.
You could intervene on everything.
Yes, you can intervene on any value at any point in the program,
right.
As long as you put an intervention point on it.
But that could be automatic, right?
Well, you could make it automatic if you want to, but then the point is also that, well, so if you want everything to kind of type check, you want that all of the holes that you're creating in the program to be typed holes, basically. And so the idea of intervention points is basically exactly this notion of type hole. So we make users add these intervention points.
Thanks.